mean, yeah, so the initial part will be the bad part.
Use that, then we use that as the seed again.
One can use that as the seed again, or one can use even the good crystal as the seed.
So are these oriented crystals?
So when we start the growth, we, as I just said, even for the seed, we use the polycrystalline rod. So we have, you know, all sorts of orientations present over there. Once a crystal is grown, then in the next subsequent growths, one can take oriented seed as well. I mean, there's no guarantee whether it will work or not, but one can always try it. And in some cases, it does work, but not always.
And even when you bring oxides, I mean, you need to maintain some oxygen overpressure, or do you have oxygen vacancies? Or?
Yes, all these crystals are grown under oxygen flow, 1 bar of oxygen flow. So there's no excess pressure that we had to apply. But in order to grow this spin ladder compound, we had to provide oxygen pressure. So it requires at least 3 bar of oxygen pressure to grow. Otherwise, it doesn't work. And you will see here that if you do a little maths, you'll see that copper valence is not exactly 2+. So this is intrinsically hole doped. So that is why it is required to have a high oxygen pressure. So these are some of the crystals that we have grown in our lab, and these are 3 papers where the details of the crystal growth.
What's the growth direction in these crystals?
So here, for instance, this is a cleaved surface, very long cleaved surface.
The is like this.
So here, this is, I mean, if you go back to the crystal, if you remember the crystal structure, the chains are oriented along these planes. Yeah.
But it's not the case in the other.
It's not the case, exactly. So, I mean, a priori, it's very difficult to tell whether the crystal will cleave in the vertical manner or at a certain angle. I mean, I think these are decided by fine changes in lamp setting and so on. You know, small temperature gradient changes can affect which grain is going to supersede the growth of other grains.
So all this because you have frozen the seed part.
Exactly, we have frozen the final float zone. We have frozen in order to analyze, in order to see what is inside. Okay, so let me now come to the crux of the talk, which is to do with the impurities. So as I said before, that it's very intriguing that there's no long range order, and yet there is a dispersion which is gapless, which means that you can excite the magnetic excitations at arbitrarily small energies. And so the question we are asking is that how this fundamental property is vitiated in the presence of disorder. In particular, I am going to talk about the finite size effects. So for instance, if you introduce a spin zero defect in the spin chain, in a spin half chain, that will cut the chain into finite length segments, all right. So you have now boundaries which were not there previously. Okay, so these boundaries behaves very different from the bulk of the material. So the other thing is that the quasi particles, they might find themselves sort of confined because of these finite length segments. So that is one thing that we are going to look at. And second is a very intriguing observation which is as yet unpublished, which is that for some specific impurities we see a crossover from a Heisenberg type antiferromagnetic behavior to an Ising like behavior. So I'm going to show you the data on these two. So first, for students, the question is, what is the ground state of an antiferromagnetic spin half chain? Okay, so probably most of you know that, I mean, I'm talking right now to the students, that there is no long range order in 1D as well as in 2D if you're dealing with isotropic spins. So in order to show you in a very hand waving way that there's no ordering in 1D, let's take this state, which is a perfectly ordered state where spins are up down up down up down, and J is the exchange interaction, which could be 80 Kelvin or 100 Kelvin depending on the system that you are dealing with. And you expect that as you lower the temperature below this scale, the scale set by the exchange interaction, you expect a phase transition, you expect your system to undergo a magnetic ordering, and that's what happens in three-dimensional magnets. So in here, let's look at the free energy of this state. So in this state, let's say the free energy is U naught. And because this state is unique, therefore the entropy associated with this state is 0. So therefore the free energy in this case is totally magnetic, all right, and we call it U naught. Now what we are going to do is, let's flip one of the spins. So when we flip one of the spins, we sort of sever two bonds. So previously these bonds were happy. This is how they want to be, up, down, up, down, up, down. But now, since you have made this spin point up, therefore these two bonds are unhappy. We are going to call them severed bonds. So there are two severed bonds. So as a result of these two severed bonds, the magnetic energy has changed by a certain amount. So that amount is, previously the magnetic energy of these two bonds was minus Js square, so that is minus 2Js square, and now it is plus Js square plus Js square. So the total change in U is 4Js square, all right. But now you should understand that in this particular state, your S is non-zero, because the system can access a large number of microstates with this much amount of energy. For example, another microstate where only two bonds are severed is shown here, and this is not the only case. You can have these two severed bonds wherever you want to, or you could have created this kink. I'll call it a kink. You could have created this kink anywhere on the lattice. So that means the entropy of the system is going to scale with the size of the system. It will have a huge entropy associated with such a change. So that entropic change can easily overwhelm the energy increase due to magnetic interactions, due to severing of the bonds. So therefore, since the free energy of F1 is less than F0, what you assume to be the ground state, therefore this cannot be the ground state. Therefore the system on its own likes to be in a state like this rather than in a state like this. So very hand-wavingly we showed that the ground state cannot be a perfectly aligned up down arrangement. Your
argument is purely a nearest neighbor argument.
Yes, that's right.
Interaction, this will not work.
Yeah, that's right. So I should point this out that we are dealing here with magnets where we have just the nearest neighbor interaction taken into account, and the next nearest neighbor interaction is not taken into account. One can do it a little bit more rigorously by writing this Hamiltonian in the form of raising and lowering operators, and then you can show, and in fact probably some of you have already done this as an exercise in the graduate school coursework, that this ground state, which is the perfectly aligned ground state up down up down up down, cannot be an eigenstate of this Hamiltonian. All right, so this is not a difficult thing to show. You can show that this Hamiltonian doesn't accept this as one of its eigenstates. So what that means is that this cannot be the true ground state of the system. Then question comes, if this is not the true ground state, what the true ground state is? So going into the details of that is difficult because it's more analytical. It was first answered by Bethe in his famous Bethe ansatz. But here I'm trying to give you a physical picture of what the ground state of an antiferromagnetic spin half chain is going to look like. So in the ground state, because you will have such flips, such spin flips, so you will have these, so these severed bonds can progress either towards left or towards right. So you will have these antiferromagnetic domains, and these domains are actually separated by these severed bonds. All right. So the picture of the ground state is that in the ground state you have antiferromagnetic domains, but the domain walls are not static. All right. So the domain walls are moving, and since the domain walls are moving even at 0 temperature, that is why this is an example of a quantum spin liquid. All right. And if you look at if you compare this to this, the net spin change between this configuration and this configuration is exactly 1. So that means this domain wall and this domain wall, and from now on I'm going to call these domain walls as the excitations of the spin half chain. So these excitations carry a net spin of half. So these are fractional excitations as opposed to magnons, which carry a spin 1. the magnons are bosons. So in 3-dimensional magnet, the spin excitations, which when you quantize the spin wave, you get magnons as the quasi-particles. Here you get spinons as the quasi-particles, and the spinons, they carry spin half. So the picture now that we have come to is the following, that in the ground state we will have these spinons, and they are moving, you know, continuously moving, and because of that we have a liquid like ground state. So we have and because you can excite these with infinitesimally small amount of energy, so therefore the excitation spectrum of these quasi particles is going to be gapless. And I have not shown it here, but the other important point is that the spin correlations in the chain decay as a power law, even though there is no long range ordering. So, yeah.
One thing, so you said that the spin difference is 1.
Yes.
It's minus half to half.
Yeah. That's right. That's right. So the total spin change is 1. So I mean, one can also do, you know, I mean, these are more fancy things which I myself don't understand, but because I read it, so I will convey it to you, and you, if you are interested, you can go back and read further. So one can do a transformation known as Jordan-Wigner transformation. So you can you know, map these spinons to spinless fermions, all right, in 1D interacting spinless fermions, and that gives you the complete mapping of the spin chain to a Luttinger liquid, and that's why it's called Tomonaga-Luttinger liquid. And these concepts we are going to use later in the talk. So now let's look at the excitations. So you measure the excitations using neutron in an inelastic neutron scattering experiment. So this is the incoming neutron. It will interact with one of the spins in the chain, and this is the outgoing neutron. So this spin has flipped, and as I talked about earlier, without any further energy cost, these walls, which are the spin half excitations, can actually move in the 2 directions. So therefore, in every neutron event, you're going to create 2 spinons. So spinons are always created in pairs, and that is why the excitation has a continuum of quantum states. So there is a lower bound which corresponds to 1 spinon at rest and the other one moving, and there is an upper bound which corresponds to the 2 spinon moving in the opposite direction, and all the quantum states in between can be accessed. And this is what? Sorry? The lower bound corresponds to 1 of the spinons at rest and the other one moving. So this is the form of the excitations which was worked out. Yeah, which was worked out by Closio and Pearson as early as in 1962. But this dispersion is a dispersion of spinons, of spin half particles, was interpreted by Fadiev and Takhtazan in year 2003. So here omega k1 and omega k2 refers to the energies of the 2 spinons, and k1 and k2 are their respective momenta. So now I have shown you that you have a chain actually behaves as, you know, particles, spin half particles, spinons, which I call spinons, or which are called spinons. So I am going to now show you some experiments where the spinons have been seen. I mean, one can see them directly in such experiments. This is a calculated spectra, but one can actually experimentally determine the spinon excitation spectrum. But the other interesting things that one can do is separation of spin and charge degrees of freedom of an electron in a 1D chain. Or one can even go further and look for spin orbital separation, because when an electron, when it is bound to a nucleus, it has a certain orbital angular momentum. So you can explore whether the spin and orbital degrees of freedom of an electron can be separated, and this was shown in this Nature article in 2012 by Justina Schlapper. So the right panel shows the spin charge separation. So this is a typical angle resolved photo emission spectroscopy experiment, where the photon knocks off an electron, creating a vacancy over here, and now because of those dagger operators, this electron is going to fill up this vacancy. As a result of this, the vacancy will move. This vacancy is essentially the charge on or the holon. This is going to advance towards the right, and the moment this happens, this domain wall like excitation is created, the spin-on is created, which is going to advance towards left. So this is how the spin and the charge degrees of freedom can be separated in a 1D lattice. Similarly, one can see the separation of spin and orbital degrees of freedom. So here the electron is excited to a higher orbital, and then the same thing happens. The electron moves to the next side, and that creates a spin-on excitation, and these two are separated. So here is the data. This is the excitation spectrum of spin-on, and these are the orbitals. Another thing which is very curious is that in these materials the spins can carry heat. So these are electrical insulators, these are Mott insulators. There is no electrical conductivity associated.
The spin excitation is gapless.
Right.
The other excitation, the charge and orbital, why is it gapped? How to understand that? It has a finite energy.
That's right. It has a finite energy everywhere, because you need a finite energy to excite the orbital to go from.
Orbital, okay, but in the case of the charge, what is that? What is that mass?
So I have not shown here the charge dispersion. The charge, I mean, the data for this experiment is not shown here. Sorry, I mean this experiment was done almost a decade back, 10 years before this experiment was done. The spin charge separation was seen much earlier using RPEST.
The charge degree of freedom, is it again massive, or is it?
I don't really remember that now that well. So, so as I was telling you that these are electrical insulators, so no electrical conductivity, but they can carry heat, and they can carry heat quite efficiently, as you can see here. So the first peak that you see, this is thermal conductivity plotted as a function of temperature. The first peak that you see here is the normal, I mean it's the phonon peak that you expect in any insulating crystal because of Umklapp processes. And then there is another peak which appears only along the chain direction, and this is actually the peak which is because of these quasi particles, the magnetic excitation. So this is the magnetic contribution to the thermal conductivity, and in fact by changing the stoichiometry of this material you can shift this peak all the way up to room temperature, and that makes it technologically very relevant, because